I'm Kasper. So I work at Grakn, and today I will be talking about things that are not. So in other words, I'm going to be talking about negation. About negation meaning, about how we interpret it, about the possible problems stemming from having negation or using negation, and about the consequences of making specific semantic choices. So negation is quite a natural concept, right? We use it every day in our natural language. Now, if we look at the query languages and the mechanism of query answering, we can basically see that this mechanism is equivalent to question answering or simple question answering. So it's a quite natural need to be able to express that certain conditions do not hold. So that's why we basically need negation. So just to set the stage, or paint the big picture of where are we actually. As you may or may not know, so the Graql query language has strong roots in logics. So we were very heavily inspired by both Prolog and datalog. And you can actually view the Grakl query language as a modern implementation of datalog, which is adopted to graph databases. So so our immediate neighbors or like technologies that are similar or that we draw inspirations from are datalog, which is a subset of Prolog geared for databases, and Prolog itself, which is a programming language. So now that we know what's the background and know the top level view picture, we can actually start talking about negation. So actually, before we do that, we need to define a couple of notions that will help us express what are the problems and consequences of negation. So the first notion is the notion of a Hellbrunn Base. So it sounds very profound, but actually what it is the following. So say you have a KB, so a knowledge base. So your knowledge base is basically a set of some constants and a set of some predicates. So now a Hellbrunn Base of this KB is simply the set of all possible ground atoms, so facts, that can be built from your constants and predicates. So for a simple example, if we just have a single constant of Socrates, and we know he's a human, and we know that every human is mortal, then our Hellbrunn Base contains only two facts. One, that Socrates is a human, and one, that Socrates is mortal. So all possible assignments of constants to our predicates. So now that we know what a Hellbrunn Base is, we can define the notion of an interpretation. So an interpretation is simply a subset of our Hellbrunn Base, which the truth values assigned to our facts. So for a simple Hellbrunn Base that we defined in the previous slide, we have two possible facts and we have two truth values. Therefore, we have four possible interpretations. So either all our facts are true, all our facts are false, or one of the facts is true. So now that we know what an interpretation is, we can move a step further and define the notion of a model. So a model is an interpretation that satisfies our clauses in our knowledge base. As simple as that. So what it means is if we take our facts from our interpretation and substitute them into our clauses, we will find that the clause is satisfied. So either the outcome is true if all the premises are true, or one premise is false, then the outcome is false. So in our example, the only interpretation that satisfies this condition is the last one. So there's only a single model out of our four interpretations. So the final notion is a notion of a minimal model, and a minimal model is simply a model that cannot be further decomposed into another model. So now that we know like the basics of the vocabulary, we can look at one of the most fundamental theorems. And this theorem actually states that if we don't have any negation in a KB, then our KB has a single and only one model, and that's a minimal model. So that's a very strong guarantee, because now we will see what will happen at the moment we introduce simple negation in our knowledge base. So let's look what happens if we add a negation. So this is like not a very exciting example, but just demonstrates the point. So we have basically two predicates, two binary predicates. One, the red predicate, the blue predicate, and we know that the red holds between 1 and 2, and 2 and 3, and blue holds between 1 and 2. So this is a simple graphical representation of what we know, what are our facts in this knowledge base. So those are our facts, and now we have a couple of clauses. So the first clause basically says that the path predicate is equivalent to the blue predicate. The second clause says that path is a transitive predicate. And finally, we define a monopoly between two entities as something that holds if the red predicate is satisfied and the path predicate is not satisfied. So in this simple example, we can actually arrive at two possible models, and both are minimal. So what actually to do with this fact, how to deal with it? So first, let's look in more detail at the models we have. So the first model actually follows quite naturally if we just substitute the information we have into our clauses. So model A is like the intuitive model for us. Now, to produce model B, what we need to do is we need to look at the clauses and try to think of facts that would satisfy them. So this is in a way, well, you could say this is an abductive approach to the reasoning. We're looking for facts that would make our clauses true. Now, even though the model A seems a more natural one, can we actually say that any of them is more appropriate? So actually, this is a very fundamental question. And in fact, it led to the so-called great logic programming schism, where we basically can either, well, we have two ways of dealing with it. The first way is actually we say that we accept the fact that we have multiple models. And the other approach is, okay, we still want only one model, so we need to come up with some model preference criteria. At this point, I realized that the notion of a model of a knowledge base might still be a cryptic idea. So the analogy I like to use is the one of equations and solutions. So say you have a quadratic equation, right? In general, it will have two solutions. Now, can we say that any of them is more appropriate, or is any of them more valid? In general, no, they're equivalent. But now say you have a system, and the system is modeled by this quadratic equation. But we have some extra context that says, okay, this is our system, but the only solutions that make sense for us are the positive ones. So in that way, we can actually eliminate one of the solutions, even though it's mathematically valid. So in a way, you can think of this procedure as something that happens if we follow the single intended model route. So this is actually the approach we took at Graql. So I'm not gonna go in detail. Well, I'm not gonna talk about the multiple preferred model. Instead, we're gonna focus on this strategy. So what do we need to do now? One, we still haven't defined what do we mean or what's the meaning of our negation, or how to interpret it. And two, we now need some model preference strategy. So a typical starting point of defining negation meaning is the so-called negation as failure. So the basic idea is actually very simple. We say that if we can infer a negative fact only if we can prove its corresponding positive fact to be false. So say we go back to our previous example of a monopoly, and we query, we want to know whether there's a monopoly between 2 and 3. So the general procedure is to evaluate our positive predicates first, so that we can leave the negative ones at the very end. And the reason we do that is because in this approach, unless our negative predicate is fully ground, so all the variables have corresponding constants, we don't have any soundness guarantees. So that's one problem with this approach. Another problem with this approach is that there are possible infinite computational loops. So just to summarize, this is the basic approach how to actually interpret negation. It imposes a strict requirement of groundness of negative facts, and it has possible problem with computational loops. Even though it has its problems, it's the basic sort of way we can interpret negation. So now we know what it means to have a negative fact. So we need to establish some model preference now. And the way to do it is to introduce so-called stratified semantics. So what's a certification, or what does it mean to be stratified? So this is basically a big word that says ordering, so ordered semantics. So a certification is basically an explicit ordering that we impose on how we evaluate our rules. Now, an important theory in that case is that if there is a stratification, all our certification will produce the same minimal model. So that serves as our model preference criterion. So that's great. So we have our minimal model, but this is all provided a certification actually exists. So how to make sure we can actually stratify our rules? And the simple answer is we look at the type dependency graph. Now, what a type dependency graph is. So if we have a sample knowledge base, so here we have 2 clauses, we simply create a graph of our predicates where we draw an edge from our hypothesis to the conclusions. So, okay, we have husband, and it has 2 dependents, the predicate of married and man, and we have single, which has 2 dependents, a man and a husband, which is the negative, that's a negative dependency. So if you look at this graph, we can actually see that, one, it's acyclic, so there's strictly no loops, and what is more, there's no loops with negation in them. And this forms our condition for certifiability. So our KB is stratifiable only when there are no loops with negation present. So these are our basic 2 blocks. That one provides the actual meaning. The second one provides some model preference. Now, how does it actually look when we compare it to Graql? Or what did we do when we were implementing Graql's negation? So we actually started with the negation as failure approach, but we realized because of the groundness requirement, it's very limiting. So the amount or the space of things we want to express is very limited. because this is actually a very strict requirement. So we wanted to go a step further, maybe try to relax it a bit. And the approach we took is we extended the notion of negation as failure to the idea of negation as a set difference. So what it actually means. So the idea is very similar, but instead of having strict requirements of our negated components being ground, we now only require that at least one variable is bound. Now, how do we do that? So let's say, let's look at an example. So in here, we actually want to know who is an orphan. So the query to actually retrieve this sort of information is basically, an orphan is someone, is a person that doesn't have a father, doesn't have a mother. So we can actually visualize the answer sets of this query in terms of sets. So then the answer to our query is basically the set difference of all the people minus the people that have a mother minus the people that have a father. So in that way, we define the meaning of our negation operator and how do we interpret it so we actually arrive at an answer. So this is the extension we did to provide more expressivity. We stayed with the stratified semantics, so that prevents us from infinite loops, as well as gives us the model preference criteria. And maybe just to mention the possible extensions, is the next natural step would probably be to allow negation actually occurring in loops. And there are ways to do it. One possible way is the so-called well-founded semantics, but I'm not going to go into that in detail in this talk. So yes, so this is all great. This is the theory of how we actually understand negation and how do we deal with it. And now I wanted to come with a more practical example that illustrates, the power, or just shows how can you use negation in practice, and which is not a trivial example. So our example is I think the well-known Sudoku puzzle. So if you don't know it, I'm just gonna briefly mention what are the rules of engagement in this case. So in general, we are operating on n by n grids. Each grid has a specific number in it. The number go from 1 to n, and we cannot have repeating numbers along a row or along a column, and possibly we cannot have repeating numbers within some subgrids of the grid. So here basically there are 6 rectangles in which we cannot have repeating numbers. So how do we actually solve it with our Quail language now? So we do the usual pretty much. We start with a model. Yeah, we start with a model. So how can we model our solution? So the simple answer is we can model it as a relation, right? So we have, so in this example, we have 3 by 3 Sudoku just for clarity, because it's, the idea is simply extendable to all the sizes. So we map our solution grid to our relation with 9 role players in this case. So each role player corresponds to a single cell with a specific value. So in this case, numbers are role players, and each number has a specific value. So for 3 by 3, we just have 3 values and 3 numbers. So that's the basic model of the problem. And now, how do we actually solve it? So the basic, the naive approach is basically just let's generate 3 by 3 grids of numbers, and then let's filter the ones that do not satisfy our Sudoku criteria. So this is accomplished by defining two rules. So we have the generative rule, which generates those grids of numbers and defines it as a possible solution. And we have a filtering rule, which basically says if there's a repeat, then we mark our solution as an invalid one. So this is the basic approach. And now, once we define the problem, the solution of the problem, how do we actually get it to solve a Sudoku? So since we are a query language, the solution of our problem corresponds to executing some query. So again, for a simple 3x3, we can just say, okay, we want a solution with some initial values at the specific cells, and we want to say that we want a solution that actually satisfies all our criteria. So we just filter like, okay, give me all solutions, but they must be valid. So that's the basic approach, but we can do better than that. So the first thing we can do is introducing the notion of rows and columns. And by doing that, we effectively introduce the notion of partial solutions. So in this case, we simply add two relations. Here they are separate, but you can see that they're actually totally symmetric, and we could have only one. But again, for clarity, it makes more sense to define them like that, so we can actually follow what's going on. And the rest of the solution actually stays as it was. Well, the rest of the model. So now this is the first improvement. What we can also actually notice is that generating all the solutions and filtering them is not a very efficient procedure. So instead of filtering, we can say, okay, so we have our rows and columns, and for each of them, we're going to make sure that they are already valid. So we can get rid of our marker, and instead, we are going to define the partial solutions as being valid by definition. So this is very similar. We just make sure when we generate each row and each column that the numbers already do not repeat. So how does our solution rule look like now? So simply we build up the total solution from all the partial solutions defined via rows and columns. So you might realize at this point that so this is a 3x3 one, but in a case of bigger Sudokus, you typically have the extra requirement of subgrids not having repeated numbers. So we might want to address that. So we introduce an extra condition of subgrid validity. So we can say that we define basically a permutation of numbers where each number is unique. So this doesn't look very clean, but that's basically how you define it. So yeah, 6 numbers, and we make sure that all of them are different. So this is a simple permutation. And now we include it in our original solution rule. So we simply add 6 relations, each relation corresponding to a specific subgrid. So this looks quite huge, but I think it's still actually, you should be able to follow. So again, 6 rows, 6 columns, and additional conditions on the 6 possible rectangles. So this is actually the extended version, the 6x6, because that's where the extra condition occurs. And again, how do we actually solve it? We execute a query. So if we have this specific Sudoku puzzle, we can simply map it and say that our initial values are these ones, and we want our full solution. In this case, we don't have the extra filtering step. So, at this point, I'm not going to actually do a demo because it's not the solving is not super fast. We haven't optimized it yet. But in general, it takes from a couple of seconds to 2 minutes. And in this case, it took around 5 minutes to solve this particular one just by executing a single query. And this solution actually concludes my talk, so if you have any questions.